so 3-4 years. And yeah, we've along the way we've had some very interesting results from char array. When I started, there were very few stars from the point of view of convection of stars. Not only one big convection cell, but multiple. Right, so I'm very glad to have grad students.
Thank you. So thank you everyone for being here, or also to those who are watching from afar. I'm going to talk today about the work I've been doing for my dissertation, and which involves imaging red supergiants over a long period of time, and also some short period of time. Got to turn that on. All right. So there's a lot of people I need to thank, but first I want to start with my committee. Thank you to my advisor, Fabian Barone, for all of his advice and patience and help along the way. Thank you also to Doug Geis. I worked with Doug for a little bit on a project before I started working with Fabian. Thank you also to Russell for his advice with proposals especially. And thank you, John Monnier, for being here and also for building Merck. Without you, this thesis could not have happened because there would be no instrument to use. I want to thank the rest of my research group as well, Caleb, Matt, Ellie, Arturo. All of you here, all of my classmates and friends, but especially some people who have helped me in moments where I really needed some help, Michelle and Crystal and Katie Gordon. Thank you, everyone. There's a lot of people at CHAR and in the department who make everything work. I want to thank all of those people. I also want to thank some of my collaborators that I've written papers with, conducted observations with, and who have exchanged ideas with me. And I also want to thank my family, my Atlanta family, my wife's family, the teams in Budners, my parents, my brother Matthew, my sister Megan, and my brother Owen, to whom I've dedicated this work. And I want to thank our cat, who's super empathetic, and especially my wife Katie. All of you people have helped us get to a point where we can see the stars brighter and larger, so thank you for your help. I'd like to start with a story. So if you go outside in the winter and you look south, you'll see the star Betelgeuse. And it's a bright orange-red star in the constellation Orion, and the fact that it's bright and orange tells us something about it. The orangeness tells us that it's cool, because an orange-reddish color means that the star is cooler. The brightness tells us either that it's large or really close. And in this case, Betelgeuse is the largest red supergiant star to us, so it's both large and close, relatively speaking. And the fact that it's large and close has made it an interesting topic, or target for astronomical observations throughout history. Whenever somebody has a new imaging technique, one of the targets they turn to test things out and get some first results is Betelgeuse. And so the story of interferometry begins about more than 150 now years ago in the mid-1800s, when Fizeau had this idea of using interference fringes to measure the diameter of stars. Unfortunately, at the time, there were no telescopes large enough to even try this. But Michelson knew of the idea, and so Michelson in the 1890s attempted this using a telescope to measure the diameters of the moons of Jupiter. And doing this, he got accurate results, but there still weren't big enough telescopes to do this on a star. So when the larger telescopes were built, Francis Peace, Michelson's colleague, and Michelson were invited to work at the 100-inch Hooker telescope up in Mount Wilson. And to this, they attached a rig that has movable mirrors on top of the telescope to create a longer baseline, more or less, to measure the diameter of stars. And they did this with Betelgeuse, and they were able to measure the angular diameter of Betelgeuse on December 13th, 1920, so almost 100 years ago. So next year will be a fun year for interferometry. And this measurement that they came up with was actually pretty close to what we have today for the diameter of Betelgeuse. So they did a great job. So the idea behind interferometry is the idea that light can interfere. And the classic example of this is Thomas Young's two-slit experiment. So you have some sort of pin source of light, point source of light, and then two slits, and the light passes through the two slits, and when it hits some observation, maybe a piece of paper or photographic film or whatnot, you see bright and dark spots. So the bright spots are is when the light is constructively interfering, and the dark spots is when the light is destructively interfering. And for this to happen, for interference to occur, the two waves need to be mutually coherent, which means that they have a constant phase difference at a point in space over a long period of time. So this is an important thing to keep in the back of your head when we talk about interferometry, this idea that we need this coherence. in Michelson's experiments with interferometry, all of the ones he did, he came up with this idea of visibility, which is the measurement of the difference in intensity in the fringes divided by the average intensity. So visibility is a key observable that we use in interferometry, and it's really useful because it gives us the complex coherence function, so the degree of coherence between the light waves. This matters because of the van Zerdicke theorem. So and this states that the Fourier transform of the angular intensity of the distribution of the source in the sky, so like what this object looks like more or less and how big it is so you take the Fourier transform of that and you get the complex spatial coherence function. So this is an example. So what you have here is just you have a disk with a little bit of darkening on the edge. You take the Fourier transform and then you get this distribution. And so what we do in interferometry is we sample amounts of that spread, and we're able to figure out what the star looks like and how big it is. Why go through all of this trouble to do interferometry? And it really can be a lot of trouble. It's not super simple. It's a great technique, but it's not trivial. Why do it? We have big telescopes being built. So this is a cartoon showing some of the largest existing and planned telescopes, including some telescopes that are just too big to be built because they're too expensive. So the notable ones you might have heard of here are the green one. This is the EELT, and the 30 meters here. The big circle at the bottom is Arecibo, which is a radio telescope. So this is CHARA. This is what we've been using. It's an optical interferometer, and you've got 6 telescopes separated in this Y configuration at different distances. The telescopes are 1 meter each. It's atop Mount Wilson, the same place that Michelson and Pease worked. So it's pretty cool to be doing interferometry, the same place that Michelson and Pease did their work. And these 6 telescopes provide light that's directed into a beam combining lab, which I'll talk about more in a bit, and you get the fringes there. So the concept of a baseline in interferometry is the separation between 2 telescopes. So you can have the baselines, on the Y configuration between the 2 near telescopes, but also long baselines between multiple telescopes that are in different arms. We have all these different baselines. And the longest baseline that CHARA has is 330 meters. So when you put the cartoon against CHARA, and this is the scale, this is what you get. So as you can see, CHARA is a much larger facility than any of these telescopes planned. And this matters because the resolution of an interferometer is given by the wavelength you're observing at divided by the baseline. So you can get incredible angular resolutions that you couldn't do with a single mirror. You're not going to build a 330 meter mirror using CHARA. And that's why we go through all of this trouble, because we want to see things that are really small or measure things that are really small, and this is the way to do it. So a little bit of technical background on how interferometry works. So say you've got 2 telescopes. Light comes to each one from the star. Because they're in different locations, the light travels a different distance and also arrives at a different time, and so you need some sort of delay to keep everything in coherence. Once you account for that difference, you send it to the combiner, and you get fringes. And so what we measure when we observe the fringes is this complex visibility, which is normalized from the visibility equation before. And you get the fringe contrast, that's the amplitude, and you also get the phase. But the phase is an issue because it shifts because of the atmosphere. So what happens is your source has some true visibility that you want to get, some true complex visibility consisting of the amplitude and the phase. But along the way, things get distorted by turbulence in the atmosphere, different temperatures in the atmosphere. There's additional phase factors added to the phase. There's also factors added to the amplitude in form of gain, but we can account for that through calibration. The phase is a little trickier. So what was developed originally in radio astronomy is this, well, first. Why does this matter? Okay, so it matters because phase contains a lot of information about an image. So I have a picture of my advisor and then a chimp. My advisor is on the left, to be clear. But what happens when you transfer the phases of these images? Everything switches a bit. So phases contain key information on what an image looks like. So we developed this in interferometry. We have this technique called closure phase. So you use a closed triangle of 3 telescopes. You get 3 baselines. And so one of the, example, baseline 1, 2 is going to contain the true phase for that baseline, what the target would actually be, plus the contributions of the atmosphere. What happens is when you combine the 3 phases, so you combine the visibilities from the 3 different interferometers, these cancel out and you can recover some portion of the true phase. So this is a really useful technique, and it's key to be, you can't do imaging and optical interferometry without doing this. Okay, so with that introduction about interferometry done, I'd like to tell you what I've been working on. So the question that I started with was, what do the surfaces of red supergiants look like? We don't really know. We don't have these images. But we have some 3D models. And so the 3D simulations show large cells. So you've seen pictures of the sun. And these pictures of the sun, the cells are small. Convection cells, granules, are quite small compared to the sun. On red supergiants, they're huge. So the convection cells are predicted to be roughly the size of the star. And the granulation can be half or tens of percentages of the surface of the star. And so the convection cells are theoretically predicted to last years. The small granules are theoretically predicted to last maybe months, up to a year. So that's what 3D models say. We want to see whether we can actually get something like this. So how was I going to do this? The goals that I wanted to achieve were see what the supergiants look like, see how variability and convection relate to what I find on the surface, and see whether these models are correct. And I was going to do this by constructing these high-resolution images, imaging the stars over different timescales, years and months, and also compare what I find to what models predict. So red supergiants, a little bit about them. Like I said, they're large and huge, and so they have a high luminosity, up to like 300,000 times the luminosity of the sun. Their radii can go up to like 1,500 times the radii of the sun, hundreds of thousands, low thousands of the radii of the sun. They're cool, 34 to 4,100 Kelvin with some wiggle room. They come from 9 to 25 solar mass stars. So these are moderately massive stars. Not the most massive stars, but certainly much more massive than a lot of the stars we talk about in this department very often, unless you work with Doug. And then they rotate slowly. So that's one of the key things. People ask, you're imaging these spots or these features, and things change over years. Is it just rotation? Red supergiants rotate fairly slowly. Their critical velocity is actually 40 to 60 kilometers per second, so they can't rotate all that fast. And the progenitor multiplicity, they come from these massive stars, right? Massive stars have a lot of companions. It's thought to be 60 to 85%, but there's only just now being a study done to really map that out. And so Catherine Nugent's been doing a lot of work in determining whether red supergiants have companions and what that might say about their progenitors. So what do we know about convection? How did we come to this idea that red supergiants might have really strong convection? So photometry was the first clue. And red supergiants can be classified into two general groups photometrically. They can be called LC, which is a slow irregular. This means that you can't really get a pattern out immediately. And the amplitudes are about 1 magnitude in variation. And then there's these SRCs, which do have some amount of period, 30 to thousands of days. And they also have an amplitude about 1 magnitude. So the AAVSO, the American Association of Variable Star Observers, has been key to studying red supergiants because they have such long periods. You can't really just like have an observing project that lasts that long necessarily. But amateur astronomers from all over the world like to look at stars and keep track of things. And so they provide an immense amount of really useful data in studying red supergiants. So thank you to all the amateur astronomers involved in this. So one way to study kind of piece out what's happening using this photometry is to do something like take a power density spectrum of the variations. And so this is what Laszlo Kiss and his collaborators did a while back. And they found within this irregular variation some peaks in the power density spectrum that corresponded to what they thought were evidence of pulsation, but also evidence of variations caused by stochastic processes from convection. So that's sort of the photometric evidence that something's happening on the surface. There's also some spectroscopic evidence. There's more and more of this. People do more and more things. In this example, what I have here are a plot of the line depth ratio against time. And so the line depth ratio basically is a proxy of the temperature. A larger one is representing some cooler material. And then the variability is these purple crosses. And so when they mapped up the changes in the ratio against the variability, they found a match. And so measurements of the photospheric radius, so pulsations, didn't match this variability. And so they've suggested, Gray suggested that this was evidence that the spectroscopy was showing material moving. So that's what convection would involve, material, cold material falling down and hot material rising up. So there's evidence that convection is happening beyond just these 3D models. So because people think that there's going to be these large features on red supergiants, they've been interested in imaging targets as well. So the first direct image of any star other than the sun was done by Hubble, and that was done on Betelgeuse. And that's what it showed. So it showed in the UV this hot spot in the chromosphere. Around the same time, aperture masking at visual wavelengths of Betelgeuse showed also some features. And so this was evidence that there's at least like large features on red supergiants. As we evolved in our technology, we were able to do more. And so John Young observed Betelgeuse again with the COAST interferometer at different wavelengths and found in some wavelength ranges there were evidence of features and others not. So that red supergiants have really complex atmospheres. So that showed that it sort of matters where you're looking if you're looking for spots, and that these spots correspond to indicators of what's happening at certain layers in the star. Xavier Hubble used the iota interferometer to study Betelgeuse once more, and this time, rather than one spot, he found two. So this is as we get improvements in technology with our interferometry, we're able to piece out what's one spot into smaller and smaller spots. Fabian Barone used Chara to study other red supergiants. So this is some of the first non-Betelgeuse images of any red supergiant, and found spots on the star T-Per, this large hot spot. So that's where we were up until like the middle of this decade. I worked with Miguel Montarguez on some VLTI data he had to image CE Tau, a red supergiant in the H-band. And we found evidence of maybe two features. He had data from November 2016 and then a month later, and they look a little different. So there may or may not be evidence of some changes. It's hard to say just with two images. But something really exciting happens when we went to a conference about imaging stars. Someone presented about some spectral polarimetric technique he wanted to use, saw Miguel's images in Miguel's presentation and said, hey guys, I need to talk. Because this is what he had. So this is using inverse imaging from spectropolarimetry to infer where spots would be, and they match up possibly really well. That's pretty exciting. So this is sort of showing the synergy between multiple imaging techniques, and I'm currently involved in a collaboration with people doing the spectral polarimetry on some of my targets around the same time that I'm imaging my targets to see whether we can repeat these results on more than one star. Okay, so how did I get my data? I used Chara. I used Merck on Chara, a 6-telescope H-band interferometer. If you weren't at Arturo's presentation, Arturo noted that this is the only 6-telescope combiner at Chara, so this is the one you want to use if you want to do high-resolution imaging. I made some modifications to the pipeline to make it easier to use, mostly just automating areas where I would normally be clicking out bad points. And I had lots of observing time, which is wonderful. Thank you so much. And the weather wasn't always great. So I observed in 2015. That was sort of the first time that I observed, and a lot of it was just learning how things work and getting an idea of what I should pursue. Tried to observe in October. Was not successful at all. The following year, I had 2 weeks of time, and mostly the weather was good. Some of it was really bad, but having lots of time, I got something out of it. Same thing happened in October. And now I'm observing with Merck X, and this is shared risk. So the pipeline's still under development, and we're making improvements to it, but none of that is going to be presented today because it's still being worked on. I also got some spectroscopy close in time to my targets, as close in time as possible to my targets, using the NASA Infrared Telescope Facility, specifically using the SPECS spectrograph, which is a lower resolution spectrograph. I had time in September. Actually, that first observing run, I was at Chara. So I was observing at Chara, or Matt Anderson was helping me observe at Chara, and I was observing at IOTF remotely at the same time. So observing twice at once. But that's what I wanted, because I wanted to have spectroscopy tell, I'm using the spectroscopy to tell what the temperature is, and I want the temperature estimate to be as close as possible in time to my imaging. So I did this not just for my primary imaging targets, but for every red supergiant that I had studied, so I could get other parameters as well. So one of the first things I did, even for stuff that I can't image, is to get diameters. And so what we can do is we can fit a function that approximates the shape of a disk, a uniform disk, or with modifications, a lim-darkened disk, to our interferometry, to our squared visibility specifically. And this gives me an idea then of what the size of the star is. And we can do this using our tool, OI Tools JL, which Fabian and the rest of the group has been working hard on. It's on GitHub, so if you're so interested in doing this work, you can download it. And so here are some of my results in terms of diameters and also when I observed some of my stars. So AZ Sig, I got different diameters for different years, but roughly 3.9 milliarc seconds, SU per 3.23, and then a whole bunch of other red supergiants. There's not a lot of diameters of red supergiants, so this is a really useful result because that can help us with understanding other parameters. And ongoing work right now is to use those diameters to infer stellar parameters of the stars. So I took literature temperatures. That's why they have different wavelength range, different error bars, which is, so this is temperature here, and you get stellar radii up this way. So I took temperatures for now, for the most part, from the literature. I tried to use just one literature result, so I used Emilio Beck's results as much as possible, but she worked in the visual to get the temperatures, and so they're going to be a little cooler than what I would be measuring in the near infrared because they're looking at titanium oxide lines. And then I used my stellar diameters and the best confidence distance from Gaia analysis done by Bayard Jones. So Gaia parallaxes, ideally you do something Bayesian to infer the distances rather than just do an inverse distance. That's why I chose to use those. That's also why the error bars are a little funky because I have errors from my data, but their analysis works with best confidence intervals, and so I didn't incorporate those. So those error bars in the y direction come only from my analysis, my measurement of the angular diameter, and also 3% of the stellar radii. So another thing about Gaia and red supergiants is that red supergiants, because they have these convection features, these large features, they shift the photocenter that Gaia would measure, and so the parallaxes are impacted by convection. And so Andrea Chiavasa did some simulations of red supergiants and determined that a low boundary of this error would probably be 3% the stellar radii. So I incorporated that error into my estimate here as well. But this is ongoing work. I plan on publishing this later this year. I want to get stellar parameters, and I have spectroscopy, so I need to use some sort of method. You could also do SEDs, but I'm wary of doing the spectrophotometry with the SEDs because these stars are variable, and I want to get as closely in time as possible. So I'm opting to use spectral inference as well instead. So to do the grids, I downloaded a grid made for red supergiants done with Phoenix by Lacan et al. Then I needed to find other ones, and it turns out it's really difficult to find grids of spectra for red supergiants. So I had to make my own. So I used red supergiant Mark's atmosphere model. So these are spherical models made specifically with red supergiants in mind, is my starting point. Then I used Trubel spectrum, which is a spectral synthesis code for Mark's, and I generated a large atlas of spectra for synthetic spectra for red supergiants. Then I also used S-Atlas, spherical version of Atlas, the ODF version, to generate 512 atmospheres. So those atmospheres didn't exist, at least not that I could have access to. And I figured out how to use it, worked with the code writers to figure out some of the errors that I found in the code, and generated a whole bunch of atmospheres, and then used the Synthi code to generate more spectra. So I have a bunch of new, never before existing grids of synthetic spectra for red supergiants across these diameter ranges, parameter ranges. So this is stuff that, because it was so hard for me to find this stuff, I want to make public. I'll make sure it's verified, but I want people to be able to find this and not have to do it themselves, because there's no reason. I mean, that uses computer and electricity, and everyone should be able to do this. All right, so spectral inference is the ideal way to get stellar parameters. You get a better understanding of the errors and the covariance involved, but I haven't had a lot of success getting starfish to work. So for now, to get some idea of results, I just minimized my models of spectra. So here's an example of the results using Mark's for SU per and AZ sig, my primary topic for this dissertation. So that's ongoing work. Hopefully I'll get starfish to work soon, and then we'll get a much better understanding of the error in these parameters. And what stellar parameters do I get by fitting to the 3 different grids of models and using my angular diameter? I find that AZ sig is about 3600 degrees Kelvin. SU per is about 100 degrees warmer. The error on the log G has to do with the how finely spaced my grid of stellar atmospheres was. So one model fit at 0 log G, another one fit at 0.5 log G, and then another one fit at half a log G, and so it just gave a huge error spread in the log G. And then again, the radii come from my angular diameter measurements, and then the Gaia best confidence distance. So that's the first part. The second part is making these images. And how image reconstruction works is basically we approach the problem with this kind of equation. So X is sort of what we want to find. It's our image. And it consists of a likelihood, which involves the data and the associated errors, and then the regularization, which is things that we know about the object that we want to sort of guide the process along the way. The two basic priors that we use in interferometry always are that the image is normalized, because that's where you're working with normalized data, and that all the pixels are above 0, because these are real objects. You don't have negative intensity in our objects. And so the goal then of these image reconstruction tools is to find the most probable image for the data and some expectations, or another way to put it would be to find the least worst image given the data. That's really what, because you don't want to tell it too much, right? So how do you do this? A lot of what I did in my work was to find ways to improve that likelihood part, getting more data, trying to get higher signal to noise, understanding the errors better, and then improving the regularization, which involves understanding which priors to use and knowing how to interpret your image so that you understand what's really a feature and what's an artifact. So the two tools I used for this were Squeeze and OI tools. So Squeeze is stochastic. It means it's random. It uses MC chains. This makes it robust to local minima, but it's slower because of that. And you have a lot of regularization options that we can use. OI tools does gradient descent. And that means it can get stuck in local minima, so you got to be careful about where you initialize the image. You have to start with some sort of image, and you have to be careful to avoid these minima. But it's really fast, and it's good to use more than one, so you can show like that you're not just playing off results that come from one particular tool. So I have a visual description of how these things really work. So looking for the best image is kind of like being a hiker lost in the woods. With gradient descent, the danger is you can get stuck in a local minima and think you've made it to the bottom of the mountain. Squeeze uses Markov Monte Carlo chains, right? Which gives you randomized movement. So it's kind of like having a drone come and pick you up and drop you off someplace random, and you take a step. So in Squeeze, we have two different ways of doing this: parallel tempering and parallel simulated annealing. With parallel simulated annealing, you got multiple chains running all at once that have different starting points. And each time they move, they go to a new spot, and then they decide whether they want to accept that move or move on to a different one. And so if the solution is better, if it's closer to the solution you want, you're going to keep it. But if the solution is worse, there's some probability you stay and some probability you move on. And then as things progress, the probability of moving decreases. And then at the end, you get the average of all the different chains, and hopefully that's close to the image you want. So parallel tempering, what happens then is information is exchanged. So this time it's like having a group of hikers with walkie-talkies, and they keep telling each other where they are. And so if they're close, then they can exchange that information and move steps by step. In the future, it might be possible to do quantum annealing. This is a technique that exists. I'm not sure how it can be applied to the imaging. I thought about it for a little bit. But the idea then is you could just tunnel through the local minima and find your solution that way, and that would be a lot faster. So this is all really difficult. Part of the problem is knowing which priors to use and how to do it. And so if you try to reconstruct some data and you use only the minimal priors, and you don't have a really good UV coverage. So if you have a lot of data points, lots of data points can make this a little bit easier. But for limited data points, you really do have to give the image some help. You get this. If you say, OK, I know it's a star, it's probably going to look kind of circular, and you use an initial image and a prior, so you force things to look kind of like a circle, you still don't get a lot. If you say, OK, it's going to have smooth features, because stars mostly have smooth features, but you say, I think they're going to be really smooth, and you use a really strong strength, hyperparameter is the strength of the regularization, a really strong strength, you can over-smooth the image. So finding that balance is tricky. And ideally, you don't want to have to be something that depends on experience. You want something that you can sort of do that doesn't depend on the person. And so I tried to work on a technique that would do that. So what I thought of was you take an image that looks something like of the object you want to study, so maybe a model of a red supergiant. You use some existing data, and you copy the UV coverage, the observational coverage, and the noise statistics of that, and you make a fake observation, and then you do a bunch of reconstructions, all with different input initial parameters, and see what works best. So you get a huge stack of images, all sorts of different images at the end, and then you need something to compare them to. So there was a study that looked at a similar problem, And they concluded that the best metric, so the best way of comparing the two different images, was to actually just use the L1 norm, which is the sum of the difference between the two. So that's what I use here. So then you have all these different results, and you compare them all to some convolved version of your source. So you got to convolve your source image down to the resolution you're reconstructing at, and you find which one is closest. And ideally, that says, okay, this is what I should probably use to reconstruct my object and see whether I can match with the simulation. But there's more to it, right? Because you also want to know whether what I'm observing is real, right? You want to know, okay, there's a spot, is it real? So another thing you can do is you can do the same sort of simulation, but this time using a uniform disk or a limb darkened disk, some sort of mostly featureless image, and then you reconstruct a bunch of, do the same, well, okay, and this time you reconstruct using exactly what you used for your image, and hopefully you don't get the same features. You don't get a big bright spot in your uniform disk reconstruction, and it looks mostly plain. That would be a strong indicator that the feature you have is not a product of the UV coverage, at least. There's also error from the reconstruction process, and Squeeze is really good for this because it does multiple chains. So you can get a standard deviation from the result of each chain, and also a mean from the result of each chain. And you can get an idea then of the spread of the results, and that will give you an idea of how reliable that output image is. So those are all the techniques that I use then when I want to study my stars. That's how I determine how to reconstruct them, and that's how I analyze whether something's real or not. So what I did for my stars was I used two different simulations because I didn't want to bias it specifically over one particular set of characteristics. So two different simulations of a red supergiant, so they look a little different. They have different convolved versions as well, so they would look a little different if I was trying to reconstruct them. And I did that simulation stack on both of those and got two different sets of parameters and reconstructed with both of those. So here's an example of one such result. This is AZ-SIG data, the star AZ-SIG from 2011. My UV coverage is here. And this is the mean plus and minus standard deviation image, as well as the image done with OI tools. So these two images look very similar. That's awesome. The uniform disk reconstruction doesn't have any of these bright features. That's awesome too. So that's really encouraging. So this is AZ-SIG for all the different years. It hasn't always looked as good. 2011 data was incredible. I'm not sure. We have ideas of what changed, but somehow, like when I started observing, things weren't quite as good. I don't think it was me. So, but here it is. So this is AZ-SIG. Its surface changes both with Squeeze and with OI tools across multiple years. So the interpretation of this, then, at least from a visual standpoint, is that it does seem like some of these large features persist a little bit longer, but there's also changes. So, but there's, one of the things that I got when I started looking between year to year is that 1 year separation is not enough, and I need to look over a shorter time scale to really see what's happening. And unfortunately, before MERCEX, I didn't have that data, so those results are ongoing. This is the same thing for SU-PER, the other star that I have time variable data for. And again, seems to be some sort of change from 2015 to 2016, from October to August. The data quality is a little different because of the amount of data we had, but bright features still there. Some of the features still seem to be there, so that's encouraging as well. One thing I'm working on now, so that I can reconstruct using the time variable data from short spans of time using MERCEX, is this idea of temporal image reconstruction. And so what we would do then is we would compare an image from 1 month to an image from another month and use sort of each one to guide the other along the way, so that if you have incomplete data, you can sort of get an idea of what step to take next. So this is an example of it. So I took a bunch of snapshots of a red supergiant, and I simulated them with different UV coverages at different times and saw how well it works. So it's ongoing work. It remains to be seen how this operates on real data, but hopefully that'll make it easier to sort of reconstruct maybe even a short-term movie of a red supergiant. That's the goal there. And that's also in prep, and that depends on the MERCEX pipeline. So, okay, you can see visually that they're changing, but you want to be a little more quantitative about it. And so there's different techniques people use. One is to look at the contrast in the stars. And so this contrast is the root mean square divided by the average intensity, so the root mean square of the intensity. This was done, for instance, by Miguel Bantargas in our paper. And these, so up here, this is the contrast, and this is radial cuts, different. in contrast to different layers of the star, or different cuts radially in the star. And what you see is the models, the ones on top, the models in the images did not come close at all. That's probably because the models don't exist for that star. There's very limited 3D models, so it's really hard to compare to models right now. And that just showed like we need to have a model that's closer to the parameters of the star if we're going to make any sort of analysis. Well, that's one way to do it. Another way is to get the 1D spatial power spectra of the image and use that to study dominant features in an image. And so this was done by Claudia Palladini on an AGB star, and they were able to infer where the size of the convection granules in that star by taking the 1D power spectra and then canceling out part of the power spectra that came from the disk of the star. And they matched results that were pretty close to theory, so that was encouraging. So for red supergiants, Freytag found a scaling relation for horizontal granule size on the surface and the the pressure scale height. Okay, so that's kind of weird maybe, but the idea with red supergiants that's been around since the 70s is that the convection cells, these convective features in a red supergiant span like the entirety of the convective zone. And so therefore you could use the scale pressure height to estimate convection feature size. And so he used this equation. This is sort of an approximation just based on stellar parameters that he came up with. And then Kiyabasa did the same thing and used that scaling relation with actual data and found that in order to make things really work, you have to modify it a little with some additional parameters of the star. And the result is that this is roughly 5 times larger than the scale that Freytag gets. So you get 5. So if you input this and multiply it by 5, you would get the result even if you don't know all those numbers. So I did the same thing. I calculated the contrast, and I also did spatial 1D power spectra of just AZ sig because those images were better. And I've only done it for one set of images so far, and we found that, so the reason I've only done it for one set of images is that when I was doing this analysis, I found that the resolution that I was reconstructing at was not high enough. So I used a reconstruction that was reasonable for Chara. I didn't want to like over-resolve the images. But it turns out that that scale is not high enough to really do this study on my stars because you need more pixels. So I reconstructed at a higher contrast or higher resolution. And then I cut out the part that has to do with the disk, and I got this result. So the idea then is that the position of this peak here would be the size of the granules. And when I do that again, there's no error there because it's just done with one set of images right now. I find for my granulation results that are pretty close to what Kiyabasa would predict using that equation. So that's encouraging both for my interpretation of those images and also perhaps for the theory. It's also interesting that with the AGBs, they found that this law worked really well. So that suggests that the convective dynamics are going to be a little different between the two stars. That's an interesting result worth pursuing as well. So full analysis of all my images is ongoing work, and that will be published soon. So what about the future of imaging red supergiant stars? Where are we going? So Chara wants to increase the number of telescopes they have. And for red supergiants, I would suggest that we do an intermediate and a short baseline because that would let us image even bigger supergiants. And bigger supergiants means higher resolution images. So I know people have a lot of other needs. So this is just me showing what could happen. OK, so if you add a telescope, a really short baseline on the S line, maybe you can move it out a little bit more to get a better triangle. And you add a telescope maybe on the W line, you might be able to image at high resolution a 10 millarcsecond red supergiant. So this is a simulation of a result you could get doing that. Another interferometer being built currently is Magdalena Ridge Optical Interferometer being built in New Mexico. And this will have 8 telescopes. And those 8 telescopes will be able to move. So you can do different configurations, which means you can have a configuration. This is one of the proposed configurations. Have a configuration that's ideal for imaging a star like Betelgeuse. So what would happen if you tried to image Betelgeuse with MROI? This. So you could get this incredibly beautiful image. Like it looks a lot like the models of Betelgeuse. That would be awesome. So the future for imaging red supergiants with optical interferometer is really promising. And it's an exciting time to be involved in this work. So thank you. Arturo? Okay, nice to meet you.
I was just, what are the times spots to be, sort of like how?
That's a great question. So theory predicts that these really large spots representative of the convective cells, and it's not clear to me, right? That's one of the things I'm trying to pursue is when I look at these images, what am I actually seeing? Because the convective cells should be huge, and those should last years and years and years. And so the spectral polarimetry images, they did that imaging process for 4 years, and they found some persistence of features that were big.